Biostat 6611, skills for the rest of your life, bootstraps and probability. It's the bread and butter, baby, what's your jam?
Good morning, afternoon, or night, Biostat 6611. In this lecture, we'll talk about simple linear regression and its best fit line, as well as how we can calculate the parameters with some summary formulas. Again, we'll introduce first the idea of a best fit and different ways we could calculate it, then introduce the formulas that we'll derive at a later date, as well as overview a bit of the notation at the end just to illustrate some of the right and wrong ways to frame different aspects. So let's start with how we get to calculating a simple linear regression and how the best fit regression line is even wound up at. So from our first lecture, we saw that we had this formula known as a regression model, or y equals beta naught plus beta 1 x1 plus epsilon, that term at the top here. The components again were the intercept, the slope, and the error term, where that error term is the difference between the observed value and the unobserved true value of a quantity of interest, such as the population mean. We also noted briefly that the predicted value that we ultimately use for inference and drawing conclusions off of is actually represented by this formula with all the hats. Now, we can break down this idea a little more and motivate how we're going to calculate that best fit by thinking about the regression line and how it corresponds to the data. So let's let x sub I and y sub I be a coordinate pair of data for the ith individual or observation where we have, let's say, 1 to n observations. Again, the difference between a fitted and observed value will actually be called a residual, which we will generally denote here in class as e sub I, which is really our sample estimate of the error, that epsilon sub I term, that true underlying difference we never really know. We can ultimately try to choose a best line that will minimize the residuals as one approach. And so we have this figure on the right-hand side where we can note a few different things. We have our y hat equals beta naught hat plus beta 1 hat x regression line formula. So that's just the solid line we see across the screen diagonally. And it's approximately trying to balance the error or residual term that we're measuring here in blue. Now we see specifically this dashed line here is that difference from that predicted or fitted value, x sub I at y hat sub I, and it's going to be the difference from that y hat to the observed actual value we have in our sample of just y sub I. And so if we think about this relationship a bit more, we can break down how these different summaries and different pieces come together to describe the regression line that we're going to derive in greater detail and describe in later slides. So what are some approaches people have considered and how we might be able to quantify the total error that, again, we don't truly know, but we're trying to measure from our sample to fit this best line? There are multiple approaches that people have proposed, and I've listed 3 here on our slide. The first one, S, is the sum of the residuals, E sub I, and that's just a very simple, straightforward approach. Because the residuals can be positive or negative, we might want to, in option 2, take the sum of the absolute value of the residuals. So now we only have an increasing amount of information, nothing canceling out, so to speak. Or the third option might be what we call the sum of squares due to error as an approach, where we take those residuals and square them. The catch here is that they're not all equally as useful. In approach number 1, the sum of the residuals, there's actually an infinite number of approaches that can be a minimized approach for S there, finding the minimum value of S. The second approach helps to solve this issue, but it's analytically difficult to work with. So it's challenging to work with that value and actually calculate these quantities of interest. Approach number 3 actually is where the sweet spot is. It's, relatively speaking, easy to use, and it also has some theoretical justifications. And this has become our standard method used to minimize the residuals. So let's dig a little more into this method of least squares, or also known as least squares regression or ordinary least squares regression. The reason it has this name is because we're ultimately trying to minimize the sums of squares due to the error. And so we see here a few things to note. First, we have SS sub error, also represented in many places as just SSE. This is really then, strictly speaking, that sum of our residuals squared, which we can rewrite as the actual definition, the observed yi minus the predicted y hat I, and square it. A further change we can make, though, is to take our y hat and actually replace it here with the beta naught hat plus beta 1 hat xi. So we're writing just the same equation in different ways because you will encounter it in different notations and different presentations depending on the problem. Another thing to note as well is that the SSE is also known as the sum of squares error or residual sum of squares. And so it has a couple different names it may go by just depending on the context in the presentation. So what's the mathematical approach to least squares? Mathematically stated, this approach will identify estimates for beta naught and beta 1, which we'll represent by beta naught hat and beta 1 hat, such that for any possible estimators, let's just call them the same beta naught hat with a little asterisk and beta 1 hat with an asterisk, so any other possible estimator we could come up with, it will be true that based on this ordinary least squares approach, what we had in the previous slide here are trying to minimize this term with our beta naught and beta 1 hats, will be smaller than whatever alternative we may come up with the beta naught star hat and beta 1 star hat. Now you might ask, how can we arrive at these optimal estimates then for beta naught and beta 1 hat? And we're going to do this in detail later, not in this lecture set, but one approach that we'll see is that we can treat the sums of square error as what we call a loss function, and then minimize it over all possible choices of beta naught and beta 1. To do this, we'll obtain the minimum or maximum of the function at the first partial derivative and set it equal to 0. Again, we'll derive these in a separate slide set later. But with that in mind, we're going to introduce some summary formulas that will come out of those future derivations. So formulas to calculate beta naught hat and beta 1 hat for a simple linear regression. And they can all be calculated from 5 summary statistics we have on the screen here. We have our sample size n. Number 2 and 3 are the sum of x sub I and the y sub I, so our predictor and outcomes respectively. Number 4 is the sum of the squared of our predictors x sub I. And the 5th is the sum of the product of each person's outcome and predictor. From those 5 summary statistics, we have our 2 equations here below that we can use to plug in those values and derive the estimates potentially by hand. We see for beta 1 hat, it involves the sums of some products of the observed value minus the mean of those predictor values x bar, or the observed outcome yi minus the mean of the outcomes, all divided by the sum of our predictor minus its mean squared. One thing we can note as well, and we have this at the bottom of the screen here, but our s sub xy is the sum of squares of our cross product between x and y, whereas s sub xx is the sum of squares of x, which we'll also see later on is connected directly to our sample variance if we happen to divide it by n minus 1. Now, once we've solved beta hat 1, we see here that beta naught hat has a pretty easy formula, relatively speaking, where we just take the mean of y minus plugging in that beta hat 1 times the mean of x. So in theory, if you were given these summary statistics, you could actually calculate the fitted regression model with just these 5 terms of interest. It is helpful to briefly note there are a lot of relationships, especially with simple linear regression, to some of the other quantities we have discussed and will discuss more in the future. But here are some interesting connections just to highlight. So first, what we can note here is that, again, we have our beta hat 1 is equal to that cross product xy, sums of squares, divided by the sums of squares of xx. If we multiply each of those then by n minus 1 over n minus 1, that itself is equal to 1, because, we could simplify it and just say it's s of xy divided by s of xx. Instead, what we're going to do is we're going to treat these as then 2 separate formulas. Here we have s sub xy divided by n minus 1 and s sub xx divided by n minus 1. The reason we do this is that we then see we actually have the covariance and the variance for our quantities of interest, the covariance between x and y and the variance of our parameter x. We can further note actually with a little more manipulation that we actually then have this representation of the correlation between x and y, that Pearson's linear correlation, times the uncorrected sample standard deviations for y and x. And in this case, the uncorrected piece means that we're dividing by the biased n instead of n minus 1 for the unbiased estimate of the variance. With this at hand, though, we can also imagine we might want to know something about the variability of our regression coefficients. And this can help us do things like calculate confidence intervals or other summaries. Before we can do this, though, we need to introduce a few other quantities of interest that we'll also see come up throughout the rest of the semester. And some of these will be hopefully a bit of a refresher from things we've already covered. For example, we have for just our outcome y, since we can think of it just as a single variable, a random variable we're collecting, we can estimate that variance as just the sum of its squares divided by n minus 1. However, we also need to introduce now this idea that for each value of x, our predictor, there is going to be a subpopulation of the values of y that are at that value of x. The variances of the subpopulations, which we'll represent by sigma squared y given x, will be estimated by this equation, which is just a slight twist on the equation for the variance. The two big differences to note is that here instead of the mean of y, we plug in the expected value of y, that predicted value, the mean essentially at a value of x. And because we're having to estimate that value at each value of x, instead of dividing by n minus 1, we divide by n minus 2 to account for the fact we have two parameters now that we're having to estimate. We see with this formula, though, down below, we can again plug in the y hat with the actual predicted regression equation, beta naught hat plus beta 1 hat times xi, which we can then note is equal to, in our numerator, the sums of square of our error divided by n minus 2, or what we call the MSE, or mean square error, and in some sources known as the residual variance, which will be a very useful term, especially when we move to discuss things like the ANOVA table and some relationships of how we calculate statistical significance for different tests. Now, what is some of the behavior of the MSE that we can expect and actually maybe take some information away from in practice? Well, first off, if our estimate of the MSE, sigma hat squared y given x, is equal to 0, that implies that the points will fall exactly on the regression line. We have a perfect linear relationship and fit. Now, more realistically, we'll have some deviation and variation in our points in a sample. So if it's a smaller quantity, then the points will generally lie closer to the regression line, which we can kind of see down below here in the lower figure of an imperfect fit. As that MSE quantity gets larger, that implies that the points will not fall close to the regression line. They'll get further and more scattered apart. And this could be due to the true variability in y given x, or potentially a lack of fit of the linear regression model we're trying to use. Again, the larger MSE we have, or that sigma hat squared y given x, the most scatter there will be in the data about that regression line. It's also useful to note that sigma hat squared y given x, our MSE estimate, is only an unbiased estimator of the true MSE if the model is correct. Again, if we have a perfect fit. Otherwise, it will be higher than the actual true fit because it has to account for the variability in our data. And so with that information behind us, we can then introduce the formulas for the standard errors for our intercept and our slope parameter. Again, if we assume a known mean squared error, we have this quantity of our equation at the top where we can plug in a truly known MSE. However, in most cases, we're going to estimate the mean square error based on our sample, and we'll use that plug-in principle to just put in our hats instead of our sigma squared y given x without the hats. But what we see here is, again, we're just really plugging in these estimates and quantities of interest, a lot of which can be tied back into those 5 summary statistics in different ways that we can derive and then use to calculate things like confidence intervals or other quantities of interest to summarize the variability of our regression parameters. And because of that, it's important to note that we have sampling distributions for our intercept and slope. Because the intercept and slope are both statistics summarizing some model or property, we can derive a sampling distribution for each. If our regression assumptions such as existence, linearity, independence, homoscedasticity, and normality of the errors are met, and we assume that we do have that known variance, then our regression estimates beta naught hat and beta 1 hat will have an exactly normal distribution, with the expected value or mean being at beta naught or beta 1 respectively, with the estimates for our standard error from the previous slide. Oftentimes, however, we estimate sigma squared from the sample as s squared, and therefore the distribution will actually follow the t distribution. Although we can note as n gets larger, it will approximate the normal distribution. Specifically, we can make a connection then to the standard normal or t distribution equivalent, where we have this property again where we take our estimate minus some null hypothesis value or true value beta 1 divided by the standard error, and it's approximately distributed as a normal distribution with mean 0 and variance 1, or in the case where we plug in that estimate for the standard error, it's approximately distributed as a t distribution. And these are the quantities that we ultimately then use for inference and getting things like p-values from our regression results. So let's briefly close with a brief review of some notation and important things to be careful with. So we have 3 different contexts essentially for the models and the types of equations we've talked about: the truth, the expected value, and the estimate we actually get. Now the truth is that original regression model we saw before, where we have the yi equals beta naught plus beta 1 xi plus epsilon I, that error. Now in theory there's a true actual value for those terms, with that error taking into account any variability around that fit. In practice, we know that the expected value of y sub I will be equal to just beta naught plus beta 1 xi because we assume that those error terms are normally distributed with mean 0 and some variance. But in practice, what we actually then do inference off of is our equation with the hats. The estimates will derive from completing that first partial derivative and solving setting equal to 0. This just is important to note because there are multiple ways we can make this wrong if we aren't careful with our notation. For example, it would be incorrect in our first bullet point here to say yi would be equal to beta naught plus beta 1 xi, because without that error term, it implies that y versus x will be fit by a perfectly straight line through all the points. Likewise, it's also incorrect to have our second point of the expected value of yi being represented by the estimates beta hat and beta 1 hat, because we know the expected value of beta or the expected value of beta hat is equal to beta. We also have 3 cases of truth versus estimate confusion, where y hat I is not equal to beta naught plus beta 1 xi, the true values. Again, we have to estimate those with the hats. Likewise, the reverse is not true, that yi is equal to beta naught hat plus beta 1 hat. And finally, the error epsilon i's are not equal to the residuals. We're estimating those errors from the residuals, but they're not equal to one another, even though conceptually we can think of them in a very similar way. And so with these things in mind, we just want to be careful moving forward that if we ask, for example, for the true regression model, we provide our point at the very top here that says truth. If we ask for the expected values we would see based on some distributional assumptions, we would want the second equation. But more practically, what we'll generally see is we want the estimate of the regression model with our hats, so we can actually draw inference based on our sample.